Good afternoon to one and all. I am Dr. Y. Sitaramaro, Associate Professor, Department of Mechanical Engineering, Gayatri Vidya Parishad College of Engineering. Today, I would like to give the lecture on the shafts in the design of machine members 1. In this lecture, we will discuss about what I mean by the shaft and what are the different types of shafts and the material used for the shafts and how do you design the shafts based on the strength and based on the rigidity. How do you know the design? These we will discuss in this class here. So in these shafts here, the shaft is nothing but a rotating machine element that transmits the power from one place to another, and the shafts are subjected to the various stresses like the tensile stress, bending, or the torsional stresses due to the combination of these stresses here. In general, the shaft is of the circular cross section and it is supporting the transmission elements like the pulleys, gears, and the sprockets here. The axle is nothing but a non-rotating shaft and which support the rotating components of the machine, but it does not transmit any kind of torque. And these are subjected to only bending, but these are not subjected to the shafts here. So twisting movement here. So do not get confusion between the shaft and the axle. The shafts are subjected to the twisting movement and the torque, and the axle is subjected to only bending. And the design of the transmission shaft consists of the determining the correct shaft diameter based on strength and the rigidity and the stiffness here. And the line shaft or the transmission shaft is nothing but the these are either for transmitting power from one place to the one shaft to the various machines through the counter shafts. And the counter shaft is nothing but the intermediate shaft we are placing between line shaft and the various driven machines which you usually find in the factories, sugar factories and various companies also. We are finding these kind of the shafts here. And what kind of material that we are using for the shafts here. The material, whatever that we are using for the shaft, is has to possess certain properties. You should have the high strength means the shaft is able to withstand the loads, various loads acting on the pulleys mounted on the shafts here. Gears may be mounted, pulleys may be mounted, sprockets may be mounted. Because all to withstand the loads, the shaft material must have the high strength and it should have the good machinability also. That means that many of the shafts are keeping the gears we are keeping and bearings are supporting. So the machining surface must be made for the gears here or the sprockets, whatever you are mounting on the shaft. So that it must have the good machinability we have to maintain, and we should have the low notch sensitivity factor. Means the sensitivity also we have to keep the keyways also in the shafts here so that the which are having the low sensitivity factor, otherwise it will sensitive to have the higher stresses in the shaft itself. And it should have the good heat treatment properties, means to increase the hardness of the surface we have to do undergo some kind of the heat treatment techniques like the hardening techniques and tempering technique that we are using in the heat treatment properties to improve the hardness of the surface of the shafts. And the material should have the high wear resistant properties, means the shafts are able to withstand the wearing capacity also. We should not be able to wear much for the higher material that we are using for high strength materials here to contain the more loads here to the stand. So that we have to maintain the high variation properties also. In general, the material used for the ordinary shafts is the carbon of the grades 40C8, 45C8, 50C4, so on we are using. Then normally we are using the steel grades. Sometimes the shaft want to possess the higher strength. We need the alloy steels, means such as the nickel we are using, nickel chromium, or vanadium, depending upon the type of application, the type of so the type of strengths what we are using or known as the height type of stresses, whatever we are using, what are the stresses in the shafts that we are using is very much important. The shafts are is nothing but the stresses in the shafts are also having we have to use the shear stress in the shafts we are using, and the standard due to the transmission of the torque, bending stresses we are using due to the forces acting upon the machine elements like the gears and pulleys. Due to the weight of the shaft, the bending stresses are also acting because the external forces are acting on the gears and the pulleys here. And stresses due to the combined torsional and bending loads. Most of the cases, the stresses are due to the torsional and bending loads. Mainly, the design of shafts are based on the two factors, based on the strength basis we are designing and based on the rigidity basis that we are designing here. So based on the strength uh, also is very much important. So based on the strength, we have considered few cases. The shaft is subjected to twisting moment or the torque, and the shaft is subjected to bending moment only. The shaft is subjected to combined twisting and bending moment. And if you consider the shaft is subjected to twisting moment, we know in the mechanics of solids in the torsion of the shafts here. So the torsion equation T by J is equal to tau by R that we know. That is where T is the twisting moment acting upon the shaft, J equal to polar moment of inertia of the shaft about the axis of rotation, tau equal to torsional shear stress, and R is the distance from the neutral axis to the outermost fiber, which is equal to D by 2. So for the round solid shaft, polar moment of inertia J is equal to pi by 30 to the power 4. And if we substitute the value of J in the equation, we are getting torque T equal to pi by 16 tau d cube. And if you use for the hollow shaft, then the J value for the hollow shaft is pi by 30 d naught power 4 minus dA to the power 4, where d naught and dA are the outside and inside diameter of the shaft, and R equal to d naught by 2. So by substituting all the values, you are getting pi by 16 tau d naught to the power 4 minus dA to the power 4 by d naught. Let k equal to ratio of the inside diameter and outside diameter of the shaft. Di by d naught we substitute in the equation 3, and we can written as the pi by 16 tau d naught cube into 1 minus k power 4. The twisting moment T may be obtained by using the relation, and by using the power transmitted by the shaft P equal to 2 pi N T by 60, and in case of belt rise, twisting moment T is equal to T1 minus T2 into R, where R is the radius of the pulley and T1 and T2 are the tension in the tight side and slack side of the belt respectively. And when the shaft is subjected to the bending moment, then the maximum tensile stress or the compressive stress is given by the bending equation already we have studied in the mechanics of solids in the theory of simple bending. M by I is equal to sigma B by Y, where M equal to bending moment, I equal to moment of inertia of the cross-section area of the shaft about the axis of rotation, sigma V is equal to bending stress, and Y equal to distance from the neutral axis to the outermost fiber. And for a solid shaft, Mi moment of inertia I equal to pi by 64 d power 4 and y is equal to t by t. If you substitute these values in the equation 1, we will get the M is equal to pi by 32 sigma b d cube. So from this equation, we will find the shaft diameter. So for a hollow shaft, we will using the relation bending moment M equal to pi by 32 sigma b d naught cube into 1 minus k to the power of 4. And when the shafts are subjected to combined twisting and bending moment, we have to use the two theories, that is maximum shear stress theory and maximum normal stress theory. And we know the tau equal to shear stress due to twisting moment and sigma b is equal to bending stress due to bending moment. According to maximum shear stress theory, we know using the equation tau max equal to half root sigma b square plus 4 tau square, and which is equal to pi by 16 tau d cube, we will find the shaft diameter. And substituting the values of tau and sigma b, we are getting tau max equal to 16 by pi d cube into square root m square plus t square. So t is equal to square root m square plus t square, which is equal to pi by 16 tau d cube. From that, we will find the shaft diameter. Thank you very much.